All right, so I believe that yesterday we established that your N was 10 and your growth rate, which is R, was 0.2. Okay, so here we have time. Now, this is on me. This is my fault. Normally, you want to start with 0, but I did not ask you to do that. My fault. But I did ask you guys to take care of 1, 2, and 3. So can you tell me what NT was after 1, 2, and 3 years? So, Risa, do you have what the population was after 1 year of growth according to the rate of 0.2 or basically 20%?
I don't know if I did it right, but I got 12.
Did you guys get 12? Riley, what'd you get for 2 years?
I got 14.9, but I rounded.
That's fine. 15, sounds good. And let's go to Reagan. What did you get for 3 years?
18.
Okay. For 0 years, that's before there's any growth, you would automatically put your original population size, so that'd be 10. Okay, so I did ask you guys to graph this. Remember, on the AP exam, you can get points by simply labeling the x-axis and the y-axis appropriately. So the x-axis is time, and we established that our time unit was years. N is your population. So here we go. Let's do 5, 10, 15, 20 individuals. So we have 1, 2, 3, 4. Okay. Well, at 0, we have 10. At 1 year, we have 12. 2 years, we have 15. 3 years, we have 18. Certainly looks to be inclining to me. Now, I think it's safe to say that if we were to extrapolate this, which means put in big, 10 years, 15 years, 20 years, you would start to really develop that J-looking curve, would really take off. This is all exponential growth. Any questions so far? Okay. So what I would like to do before we move on is a brief review of yesterday's class to make sure that we all understand, because today we're going to continue exponential, but we're going to continue on to logistic. So yesterday we started exponential growth models. Exponential growth is the same thing as unlimited. If you went to Olive Garden and said, I would like exponential breadsticks, that unlimited breadsticks, keep them coming. The reason why it's exponential is because there's no carrying capacity that is factored into this type of model. What I put carrying capacity. And carrying capacity symbol is K. We're going to be using that a lot today. Well, carrying capacity is simply how many individuals an ecosystem can support. My little ecosystem that I call room 232 can only support 30 individuals. So it's an actual number. Downstairs, the pond, so far, I've been able to manage 8 turtles. Maybe I can do a few more, but it seems to be working great with 8. Plain High School currently can accommodate about 2,500 students. But imagine that we built some brand new buildings. We can have a lot more students. The carrying capacity goes up. Or the opposite, South Hall burns down. Our carrying capacity is now lowered. So the carrying capacity is not a static measuring stick. It can go up, it can go down, it can stay stable, and we'll play with that today. But the carrying capacity is composed of these things called limiting factors. Limiting factors is exactly what the name suggests. It influences how long individuals can live and how many individuals can actually be in a given environment. There's 2 main categories of limiting factors. One is called density dependent. And the other is called density independent. Now, when you hear density Dependent. Density is in reference to the population size. You ever heard the question, if a tree falls in a forest and no one is around to hear it, does it really make a sound? Think about that. It's supposed to be a little philosophical thinker. Well, is a wolf really a predator if there's nothing there for it to hunt? Or the proper word would be to predate. Think about that. Is the disease really infectious if there's no one around to infect? Are you really going to be competing with something if there's nothing there to compete? The door is open. As I was saying, density dependent can only happen if there's actually life there present. So this would be predation. This would be disease. And this would be, what am I looking for? Competition. Jet can't fight someone for his food if there's no one there to fight. Shane can't go fishing and catch fish if there are no fish. And you can't spread COVID if there's no one around to catch it. However, density independent will happen whether life is there or not, and that's generally disasters. Fire, earthquake, tsunami, hurricane, tornado, asteroid, supernova, whatever. By the way, speaking of COVID, as I texted you all last night, I got more than 10 emails saying so-and-so has been quarantined. Either students have it or they sit next to someone who have it. That spring break surge seems to be getting here. So if in the event you guys do get that phone call, watch the YouTube, making lessons on a daily basis. Don't get left behind. You're not on vacation. You're still in school. You just do it from home. And yesterday I gave you guys the equation. Looks like this. No, wait, that's not what I gave. Wait. Yeah, I didn't give you that one. Wrong one. My bad. Let me get the right one here. I'm giving you a different one today. It's actually going to be a whole lot easier. I think you'll appreciate it. Here it is. Well, I was looking over the AP Biology formula sheet, and they do not give you this equation. So we're going to change it. And I think you'll like the fact that I'm changing it because I'm going to give you something a little more manageable. Although this is not unmanageable, but I'm going to give you something a little simpler. So let's get into today's lesson. Today is going to be continuing exponential growth. We'll take care of this first, then we're going to get into logistic growth. All right? All right. So I'm going to change something up for you all. R represents growth rate. It's just how many individuals, how much is the population growing or not growing over time. That's all. It's a rate. And in order to calculate this rate, you're going to do births minus deaths over the population size. The difference between births and deaths over the population size. Now, yesterday we factored in immigration and emigration. That is not on the AP formula sheet. We can make do without it. So we're not going to factor it in. I'm not going to give you guys more info than what you need. I want to really help you stick with what you're going to require. So birth rate minus death rate over the population size is going to be your growth rate. So I'm just going to make up some arbitrary numbers here. We're going to, since we're so close to Easter, let's do bunnies. Let's just say the birth rate is at 5 individuals. So every year there are 5 bunnies being born. And let's say the death rate is 2. The initial population is 2. Can you guys please calculate your growth rate for me? If you're on a computer right now, I hope you're following along with us and not distracted by other topics. Avery, can you tell us what our growth rate is?
1 second.
Was it?
1.5.
How'd you get that?
I did birth rate minus death rate
Which is 3.
divided by 2.
Oh, you know what I'm going to do? Stupid. I'm going to change our growth rate to 10. Or, excuse me, our population size to 10. My fault. I don't know where I got 2 from. I'm doing that later. Do that one more time for me, Avery.
So then 0.3.
That's what I'm looking for. Okay. So R equals 0.3. There we go. And N represents population. Okay. So I'm going to teach you 2 new equations. You can use either one, but I'm going to show you how one can be a bit more advantageous than the other. Okay. So let's make a data table. It's going to have 2 columns. This data table is going to have time, and it's going to have population size. And we're going to have time 0, 1, 2, 3, 4. Now the other 2 we'll do momentarily. I'm going to leave those last 2 boxes open. And so here is what I want you guys to do. Hold on a second. Okay. On the AP Bio formula sheet, now I'm going to get you all a copy of this so you can get yourselves familiar with it. It doesn't say delta N. It doesn't do this. Don't write this down. Do not write this down. I'm saying that means change in population size or change in time. But that's not how they write it. Here's how they write it. I mean, where was that? Where's the letter D come from? What letter does delta begin with? D. That's where they get it from. Now, this right here simply means the population growth rate. This is what you're going to be seeking. What is the new population size every year? Okay? So this is the first equation I want to teach you is R times N. That's simple. R times N. So I want you to use R times N for years 0, 1, 2, 3, 4. And I will work with the first 2 with you. Okay? So year 0. Actually, we're going to start off with 10. Excuse me. So year 1. 0.3 times 10 is 13. That's it. So please, all you do is multiply the growth rate times the new population. So I'll do year 2 for you as well. So please look up here. I want to make sure you guys understand what I'm doing. So year 2. 0.3 times 13. Why 13? That's your new population size. So 13 times 0.3, I think is going to be somewhere in the neighborhood of 17. Let me check. Okay, here's what we got. Your answer is 3.9. We can round that to 4. What was the population size after 1 year? 13. So you're going to do 13 plus that 4 equals 17. There's your new N, 17. Let me show you that again. A lot of you are visual learners. You hang on every word I'm saying. So after year 1, I got 13 years. That's my new N value. I then do 0.3, my growth rate, times my new N value, which is 13 individuals. And out of that, I got 3.9. That means, here's what that 3.9 means. This is the amount that the population grew by. It increased by 3.9. Well, I'll tell you what. We can go ahead and say that's 4. I want you to round that number to whatever the closest whole number is. So we're going to say that's 4. So my population increased by a factor of 4. So I'm going to just add 4 more to it. So 13, which was my old, or my new population size, plus 4 is going to give me a new population, or new N, which will be 17. So after 2 years, the population increased to 17. Yes, Sage? So what? Yeah. So can you guys go ahead and do years 3 and 4, and I'm going to show you an alternative to this, which can perhaps be even more ideal. So do the years 3 and 4 for me. I'll give you a couple minutes. Take attendance here. Develop that muscle memory, everybody. You do not want the AP exam to be your first go through. Yeah. Yeah. All right. Sam in here. Mackenzie. Andrew, John, Sage. Malia, what do you have for the in value for 3 years? 22, that sounds about right. Mackenzie, what do you have for 4 years? Okay, I'll give you a second. Go ahead. What was it? 0.3 times 22. Okay, so it went up by 6.6. Go ahead and round that to 7, then add that 7 to the 22. 29 sounds good. Okay, so everybody, here's what I want you to do. Let's graph it. Easy enough, right? Let's make our y-axis. Let's make our x-axis. We're going to go by 2s. 2, 4, 6, 8, 10, 12, 14, 16, and so on and so on. And I'm going to go by 5s for my y-axis. 5, 10, 15, 20, 25, 30, 35, 40. Okay, so let's plot out what you guys found. At 0, we are at 10. At 1 year, we're at 13. 2 years, we're at 17. 3 years, we're at 22. 4 years, we're at 29. So far, looks like it's exponential to me. But here's the issue with this equation, R times N. What if I asked you to find 10 years and 30 years? Well, if you were to use this equation, everybody, you would have to do 5 years, 6 years, 7 years, 8 years, 9 years, then get to 10. That's a pain in the butt. And you have a time test. You don't have time for that. And then if you had to do 30, I mean, get real. You got to go 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 30. You don't have time for them. So there's a different equation that you can use where you can actually plug in the value for t and find out whatever the projected value would be for that year. Let's do that. So this is going to be dn over dt equals n times 1 plus r to the t value. R is your growth rate, T is time. Now, let me make this very clear, guys. Listen up. That is actually N naught. This is your original population or your initial population. So in our case today, you are going to put 10 for in every time. Yes, Sage? I suppose so. But plug it in and see what you got. So here's what I want you to do. Put in for T, put in 10 and put in 30. See what you get. So I'm going to erase this work here. Did you get approximately 138? Then you're going to put 138 right there. So by the time you get to 10 years, you're going to have 138 bunnies. Do 30 years now. Did you get 26,200? Exponential growth, guys, no carrying capacity. It just blows up in population. So here's why this equation is more advantageous if you have a problem like this. The time unit, or the unit of time, can be factored into the equation. Now, word of warning, alert, alert, alert. This is on the formula sheet, what I'm about to write. This is on the formula sheet, check. This is not. So on the AP exam, if I asked you, or College Board asked you to do that very same table, if you just used R times N, you would have to find the years 5, 6, 7, 8, 9 in order to get to 10. And then you have to do 11 through 29 to get up to 30. You only have 90 minutes. That's going to take way too much time. I would recommend that you use this equation instead. Okay? All right, let's move on. Let's get to logistic growth. The logistic growth model is all about factoring the carrying capacity. It was not a factor in the exponential growth model. Things just blew up and there was no stopping it. Population just exploded. But the carrying capacity definitely limits how many individuals that you can actually have in a population. So let me show you how this looks on an actual graph. Here we have time. Here we have population size. Now, everybody, let me be very clear about this. Right now, in a logistic growth model, hear me now, there is an exponential growth phase, but it's not indicative of the entire graph. because eventually it plateaus and it levels out. This is sometimes called an S curve because it sort of kind of represents the letter S. Well, the reason why it's plateauing at that point is because we have the carrying capacity. The carrying capacity is going to limit how many individuals can actually be in the ecosystem. Typically, if a population exceeds the carrying capacity, the death rate will be greater than the birth rate. You're going to have a crash. So this carrying capacity is a number. So let's just say that we're in a forest and there are deer in the forest, and this forest can support 100 deer. So K equals 100. Well, there's a forest fire and half the forest burned down, so it stands to reason that the forest can now only support half of the deer that there originally were. So this is the old carrying capacity. Here's the new carrying capacity. What will happen to the population? It's above the carrying capacity, so it is now going to crash a little bit. It goes down. It rebounds, and then it starts to develop an equilibrium with the new carrying capacity. Well, let's say some years later, the forest is able to regenerate, and it comes back even bigger than before, and now its carrying capacity is actually 150. So it's way up here now. What will the population do? It'll likely experience an increase. But look at this. It went past the carrying capacity, so it's going to crash a little bit and reestablish that equilibrium. So what I want to explain to you is that the carrying capacity is not a stable, rock-solid number. It can alter as the environment alters. Yes, Annie? No, not typically. Okay, so this is all about the presence of those of those limiting factors, density dependent and density independent factors. This is also how K strategists get their name. K strategists have a limit to how many offspring they can have because they use so many resources to help raise their young. They have so much more energy, so much more involvement that there's a limit to how many offspring that they're able to produce. When it comes to an R strategist, they just do that exponential curve. They have as many offspring as possible because they really exert no energy in developing them. All right, so what I would like for us to do is I want us to do a brief table with exponential growth, and then I want to use some of the same figures for a logistic growth. So let's do an exponential first, and then we're going to use some of the same figures to do logistic growth. So we're going to do some bunny rabbits. And we're going to start off with 2 little bunny rabbits. So N equals 2, a mother and a father, male and a female. They're going to reproduce. So we need to calculate the birth rate minus the death rate over N, which is going to be our R value. R is growth rate, B is births, D is deaths, N is the whole population. I'm going to tell you that our birth rate is going to be 2. Our death rate is going to be 0. Can you tell me what the growth rate is? Duncan? 1. Now, I want you all to remember this. A little bit ago, we did 0.3. Don't write that down. Just pay attention. What percent is 0.3? 30%. What percent would 0.5 be? 50%. What about 0.99? 99%. What is 1.0? 100%. If you have an individual, or excuse me, if you have $100 and you increased your money by 100%, you basically doubled what you had. You now have $200. You gained 100% of your money. So you doubled it. Well, that's what we're doing here. The growth rate is 1. So you're generally doubling the population. It's going from 2 to 4, and then 4 to 8, 8 to 16, 32, 64, so on and so on and so on. So let's actually put this into a chart. You're going to have 3 columns and 5 rows. We have time. We have in. And we have the population rate change. Times 0, 1, 2, 3, 4. Well, we're starting off with 2 individuals, so we can go and put 2 in there. Now, for the change in the population size, you guys can choose whichever equation you want. You can either do this, or you can do this. You should get the right answer for either one. Let's go ahead and finish off year 0, and then I'll let you do 1, 2, and 3, 4 on your own to get that practice. So I'm going to use this equation. My population is in. I have 1 plus 1. My growth rate is 1, and I'm at year 0. So 1 plus 1 is 2 to the 2 to the 0 power, and you've hopefully learned this in algebra. 2 to or any number to the 0 power is going to be what? 1. So 2 times 1 is 2. This number here is how much the population increased. So the population increased by 2. So we started off with 2, and now we have 2 more bunnies. How many total bunnies do we have now? 4. You're going to put 4 right here. So basically, every new line on the in column is going to be the sum of the 2 numbers in the previous row. So I'd like you to go ahead and solve for lines 1, 2, 3, and 4. Let's see what you get, and we will move forward from there. If you feel like you're stuck, take a look. I'm going to do a workout year 1. Here's year 2. Year 3. Because that's my original number. You use for this equation, you always start with the original number. Yeah. Yeah. Ayla,
And the number in the interval
that's just how much it increased by. Okay. Yes, Andy. No, this is just because the growth rate is 1. The reason why the numbers are identical to each other is because the growth rate is 100%. So if you had 2, you're going to make 2 more. If you have 4, 100% of 4 is 4. So you're going to make 4 more. That's just because the growth rate was 100%. If it was 2, if it was 0.2, it would be different. If it was 0.35, it would be different. This is just, I know you guys, I know what it's like to be hanging on every word when you're trying to learn something new. The reason why these numbers are the same is because the growth rate was 100%. If Jet was in a business where he increased his total money that he had every year, in year 1 he has $100. He's gonna, by the end of the year, he gains another 100. That's 200. So year 2 he has 200. 200 and 100% of 200 is another 200. So now he's up to 4. So he has 400. 100% of 400 is 400. Now he has 8. And that's just how the growth rate is when you have 1.0. Okay, now, as you can probably imagine, just by looking at the numbers, the growth rate is going exponentially up. It will continue on this trend. With 32 to 64 to 128 to 256, it's just going to just explode. Well, now we need to factor in the carrying capacity and what this is actually going to do. So let's get into the logistic model. The equation that you have available to you for the logistic model is as follows. This is given to you on the AP Biology exam formula sheet. I'm looking right at it. R is your growth rate. N is your population size. And K is your carrying capacity. Your carrying capacity is an actual number. It's not a ratio. It's not a funky equation. It's just a nice solid number. And so as we've already established, your N value is 2. We started off with 2 bunnies. The growth rate is 1, which means you're actually doubling your population every year, theoretically. But I'm going to give you another value, just a made-up number. I want to really convey this to all of you. The carrying capacity can be any number possible. My classroom's carrying capacity is 30. Downstairs, the turtle pond is 8. We're just going to use 10. 10 is a nice, cool, easy number to work with. So the carrying capacity is 10. What this means is that this environment can only support 10 bunnies. So what we would expect to see is as the population creeps closer and closer and closer to 10, do you think the growth of the population is going to increase or accelerate or decelerate when the population number is getting really close to that carrying capacity? Is it going to keep going up or is it going to start to slow down? What do you think? It's going to slow down. So let's do this. You're going to need a data table with 4 columns. This is just going to help you keep everything organized for you. We're going to have time. We're going to have a population size. We're going to have K minus N over K. And we're going to have the change in the population. Zero, 1, 2, 3, 4, 5. All right. So your population that you start with is at 2. Let's go ahead and I will work on the first maybe 1 or 2 columns with you. We have about 8 minutes left. So I've been telling my classes I want them to finish off this chart. You guys might be able to do it before you leave here today. All right, so let's figure this out. Let's do year 0, okay? So at year 0, we have, where's my equation? There it is. At year 0, we have our growth rate of 1. That's R. We have our population size of 2. That's N. We have K minus N over K. What did I say K is going to be? 10 minus 2 over 10. All right, let's show our work. 1 times 2 is 2. 10 minus 2 is 8. 8 divided by 10 is 0.8. So, everybody, this number right here, 0.8, put that into your table just to keep your work nice and organized. 0.8, there it is. And let's see, 2 times 0.8 is 1.6. This means that our population increased by 1.6. There's your entire first row. Pretty straightforward. But here comes the little trick that I really think that just a lot of practice will really get you better and better at, okay? In this box right here, for N at 1 year, you need to add the value of N and the change in N over time from the previous row. So let's go to Malia. Use your mental math here. What is 2 plus 1.6? 3.6. You're going to put that right here. 2 plus 1.6 is 3.6. And so now you're going to plug in 3.6 into the N value. And I'll do year 1 with you. And I want you guys to do 2, 3, 4, and 5 on your own. So we have 1 times 3.6, 10 minus 3.6 over 10. 1 times 3.6 is 3.6. 10 minus 3.6 divided by 10 is 0.64. So over here in my table, I'm going to write 0.64. And then back over here, let's finish solving it. 3.6 times 0.64. I've got 2.3. And so now you need to add 2.3 and 3.6. That's going to be about 5.9. What did I do? Huh? Ayla? You see what I did? Okay. So if you guys could please complete the data table. And I want you to plot it. Make a XY graph. Same values. Same titles for the axes. You have about 4 minutes left in class. You might be able to finish. When it gets boring, then you're getting it. Remember that. Whenever work gets tedious, then you know what you're doing. So boring is a good thing.